Welcome to the winter term of 2016. It's a pleasure to be here and to introduce our Jones Seminar speaker, someone who I hope everybody will recognize. He has not come very far, just a couple floors from the building. One floor. Professor Jifeng Liu is our speaker today, and it's a pleasure to have a Dartmouth or Thayer professor give a talk. Jifeng was just reminding me he hasn't given a talk here since he applied for the job 6 years ago, and now we get to see what he's been up to for the last 6 years, I think. Let me just refresh you. Jifeng has received his BS and MS in Materials Science and Engineering at Tsinghua University in China, and went on to get his PhD in Materials Science and Engineering at MIT in 2006. He stayed there to do some research prior to coming to the Thayer School. His major research field is nanophotonic materials and devices for energy sustainability, including silicon photonics for ultra-low energy photonic data links, as well as nanomaterials and nanostructures for solar thermal and solar photovoltaics. Here at Thayer, he teaches Engines 24, the science of materials, Engines 131, the science of solid-state materials, and Engines 134, nanotechnology. Jifeng has 59 peer-reviewed journal papers and 56 conference papers, 6 book chapters, and 10 granted U.S. patents, all in the area of nanophotonic materials and devices. In 2013, he received the National Science Foundation Early Career Award Development Award, and he is now a senior member of the IEEE. And the one thing I've noticed about Jifeng since I've known him is that I've never, ever seen him without a smile on his face. I've actually seen him even arguing with other faculty members with a smile on his face. I think it's probably the most dominant characteristic of Jifeng that I know, and I think so. Please welcome Jifeng.
Thank you very much for the kind words, Brian. So yes, I do like to smile because there's light. Sunlight always makes us getting excited. So it's even more exciting to have research related to light. So today we're going to share you with our research on nanophotonic materials and devices for harvesting energy from light, and also use light to transfer information energy efficiently. So actually I'd like to get 3 hours to go through all the research work in our group, but I have to limit myself to about 50 minutes. I probably will go a little bit over time. So I selected 3 topics. The first one is basically high energy efficiency data communication and high efficiency solar cell at low cost. So seemingly they have no connections, but actually we found out that there's a material fabrication technique, which is basically high quality crystallization of germanium tin alloy on amorphous substrates, is a key to both ends. We'll tell you this story, which leads to my NSF Career Award. And second topic is basically talking about how you can absorb the most light with the thinnest absorber layer. So basically, we're trying to utilize less and less solar material to reduce the cost of solar energy. But as you know, a very thin layer doesn't really absorb much light. So we have to introduce some nanostructures to trap the light inside that thin absorber. So here we're introducing the self-assembled nanoneedle structures, tin monoxide electrodes. It provides not only efficient light trapping to thin films, but also down to the thickness of 1 atomic layer thickness, as you see here. Basically, if you put this material on graphene, which is a single atomic layer of carbon, you can actually clearly see the outline of this transferred graphene layer. We'll tell you how that works. And in the third topic, we're going to complement the solar cell technology. As we know, the sun doesn't shine all the time. So if you want to use solar energy when the sun is not shining, there has to be some easy energy storage approach. Turns out it's much easier to store heat compared to storing large amount of electricity. So that's why people were investigating solar thermal technology as a complementary approach of harvesting solar energy. In this case, it's critical to have a selective absorber that maximizes the solar absorption with minimal thermal radiation losses in the infrared regime. So that's the work basically related to nickel nanochains. So basically, nickel nanostructures we use can be applied to absorb the light, sunlight very efficiently with minimal thermal radiation losses. So here's a brief outline of the talk. So in the first topic, we're going to discuss about this interesting relation between high efficiency data communication and high efficiency solar cells. We'll talk about their challenges. We'll tell you that basically we find the key to both laws. Basically, if you can grow high quality germanium tin on amorphous materials, that will help you to solve both problems. So before we go to the introduction to the first part, the challenges in energy efficiency of information and communication technology, I want to ask the audience, can you give me an estimate how many devices do we have in this world that are connected to the internet? Any guess? 100 million, 1 billion, 10 billion, 100 billion? It's currently 25 billion. The world's population is 7 billion people. So on average, every one of us carries 3.5 devices around. So we can easily count those. We have probably 2 desktops, 1 laptop, and 1 smartphone. So that's already 4. So and also there are some devices probably just hanging around there. So we have so many devices that actually the data traffic from mobile communications is increasing exponentially in recent years. So this chart is basically from Cisco talking about the data traffic from the mobile devices per month versus year. So these years are basically projections. So first of all, you can see this is increasingly at a very high rate, 57% per year. And also the absolute number is huge. If you look at per month data communication just from the mobile devices, that's about 5 exabytes. 1 exabyte is 1 billion gigabytes. How much is that information? Well, if you look at the information human beings have generated in 5,000 years of history before the 21st century, that's only 12 exabytes. Currently, in 2.5 months, we can actually catch the same number. So all those communications require a lot of facilities from information and communication technology, which is ICT. For example, data centers is a big component there. So here's the photo of a data center. I believe this is in San Antonio, Texas. So you can see this is a pretty grand scale data center. You have all the servers inside. Each of this data center consumes 100 megawatts of power. So the current standard is actually 128 megawatts. So how many do we have in the United States? Well, here's the distribution. According to this website, we have at least 1,700 of those in the United States. So it's no surprise that all these add up to a very large energy consumption of electricity. So if you look at the percentage of electricity consumed by ICT in the United States, back in the early 2000s, that's only about 2%. Nowadays, it's almost 10%. So it's growing at a very fast rate. And if you look at data points collected from literature, it's quite linear increase in the percentage. And that transferred to a large carbon footprint too. If you look at the CO2 emission from ICT back in 2012, that's about 530 million tons. That's larger than 3 countries combined: Argentina, the Netherlands, and Malaysia, with a total population of 87 million people. And you compare to industry, amazingly, this is even higher than the CO2 emission from the steel plants. So you can see that ICT power consumption is already becoming a very interesting issue for the engineers to address. Of course, the ICT industry are fully aware of that. If you go to the data center web page of Google, here's what you see. So basically, they're saying harnessing our data to drive efficiency. They're talking about using the data to better use the energy. So basically, the whole industry is understanding this challenge. But interestingly, when you look at this web page, it's not really showing you the computers in the data center. Actually, it's showing you a lot of ugly tubes here. What is this for? Any guess? cooling, exactly. So when you have so many computers and you run the current through the electrical wires or cables, it generates a lot of heat. That by itself is a decrease in energy efficiency. And after you generate all those heat, you don't really want to burn your data center, right? So you have to cool it down, and that cooling and air conditioning takes even more energy. That's why, starting from 7 or 8 years ago, people are starting to substitute these metal cables with optical fibers. So when the light transport in this optical fiber, because it's this transparent media with very, very low loss, so you don't generate any heat, there's no resistance capacitance delay either, so you can get both high speed and high energy efficiency. And people now have basically substituted connections between the boards with optical fibers, but turns out that's not enough to further drive the energy efficiency. So that's why earlier this spring, actually last spring, Microsoft, Intel, and with some other giants in the ICT industry, started a consortium for onboard optics. So basically bring optical components on board to communicate between devices. And eventually this push is going to lead to the core-to-core communication on the same chip. So photonic integration is a great way to increase the energy efficiency of communication. However, it's not a trivial thing to do. So if you look at the integration scheme, basically because we want to integrate with electronics, so the best platform will be silicon. However, silicon itself is not very good light emitter or absorber. So therefore, you have to integrate silicon-compatible materials on this high-quality silicon substrate. So that's why for the past decade or so, many researchers, including myself, were studying growing silicon-compatible materials like germanium on these high-quality silicon layers, basically introduce photonic functions there. This is okay for low degree of photonic integration. If you want to go high degree, large scale integration, basically you find there's a trouble if you look at the size of the photonics compared to electronics. Photonic devices are limited by the diffraction. So that's why the size cannot be too small, otherwise it doesn't confine light. So 500 nanometers is already considered nanophotonics from the photonics point of view. But if you look at transistors, which are the brain cells of our chips, basically at that time it's already 32 nanometers. Nowadays we are 22 and moving on to 14 nanometer. So there's a big size mismatch, so each of this photonic device takes a ton of area on this electronics real estate. So the best solution will be move all this photonics to the interconnect level up here, basically above the CMOS. However, although you can do something like chip mounting with a photonic chip and silicon, those photonics chips from what we call 3-5 semiconductors, basically a compound between the elements in group 3 and group 5 of the periodic table, those materials are having actually poor mechanical properties. So you're never going to grow wafer as large as silicon. So when you do this kind of bonding, you cannot do a wafer process. You have to do a chip-to-wafer process. That lowers the yield and makes the process complicated. So the ideal solution would be if you can introduce some nice photonic material compatible with silicon directly on these upper layers. However, you have great challenges. All these layers that's insulating the metal wires are basically amorphous material, which has this order. While now you want to grow a high-quality ordered crystal on top. And also you have to do this at low temperature, because once you have the metal down, your temperature cannot exceed 450 degrees. So that poses a great challenge. So this slide basically gives you some more background what I'm talking about. If you look at the crystalline materials, basically they're composed of these unit cells, and if you repeat these unit cells in a completely order across the entire piece of material, that's what we call single crystal. So single crystal silicon is basically what we use for making the high-end electronic devices. On the other hand, there's another extreme where there's almost no order at all. So I say almost no order because the order is very short range, within a couple of unit cells. So this is what we know as amorphous materials. So now if you have a amorphous template, if you want to grow single crystalline material on it, that gets very complicated because there's no template you can utilize. There's also kind of crystallinity basically sitting in between, which is what we call the polycrystalline materials. They're composed of different grains, each grain can be considered as a tiny single crystal. However, they are having different orientations. So whenever they meet, you have a boundary that's not perfect. So if you want to get high crystallinity, you want to get as big grain as possible. And that requires extensive atomic diffusion. However, at 450 degrees for most of the semiconductors, it's too low to get this extensive diffusion, so it's hard to get the large grains. So that's the challenge we're facing. So now we're talking about another challenge that eventually will converge to the same material system. So this challenge is basically how you make high-efficiency solar cells. So when I teach 174 lectures on the solar module, every year students will come up to me saying, why can't we make a solar cell that's 80% efficiency? And I said, the short and artistic answer is that the sunlight is colorful. So what does that translate into scientific language? Well, the sunlight is having a very broad spectrum from UV all the way to the infrared regime, almost extending into mid-IR. So if you just select any single material to capture the sunlight and want to convert it to the electricity, you always have quite a bit of loss. Take the silicon as an example. So this is the theoretical curve for perfect silicon when you use to harvest solar energy. You see that we waste a lot of the photons in the IR regime. That's because those photons has energy smaller than the band gap. So when this kind of photon come in, they don't have enough energy to excite an electron from the valence band, which is the ground state, to the conduction band, which is the excited state. So they just go through without doing anything. This part is wasted. Now you can tend to think of the opposite. Okay, now let's absorb all the sunlight with a very small band gap semiconductor material. So let's set the band gap here, right? Everything is absorbed. What's wrong with that? Okay, you see that even for the photon energy greater than the band gap of silicon, you still have a big loss. And the loss comes like this. Let's say you have photon energy, much greater than the band gap of the semiconductor. Comes in, no problem, excite electron hole pairs here and here. But because it has so much energy, it actually exciting the electron quite high above in the conduction band. And the hole is relatively deep in the valence band. While the energy minimum in the conduction band is actually here. So what happens is that they will readily release their excess energy. So this used to be a hot electron because it's high energy. This used to be a hot hole. Now they have a tendency to lose their energy. After doing so, it's called thermalization. So basically, any photon energy that's greater than the band gap is going to be lost. And that part is being lost to heat. Therefore, if we have a tiny band gap semiconductor, or in the extreme case, like a metal nanostructure, as we'll talk about later, that's a great way to convert solar energy to heat, but not directly to electricity. So if you choose any single material to absorb sunlight, single semiconductor material to absorb sunlight, you'll find the efficiency never exceeds 31%, and that's basically the limit here. Okay, so to deal with the broad solar spectrum, people are thinking about different methods. So if one semiconductor material is not good enough, let's stack different semiconductor materials with different band gaps to cover the broad solar spectrum. Each material convert a slice of the solar spectrum such that each piece is efficient, and then you sum them up. So that's a much more efficient way to make solar cells. The complication is this. If you want different band gap material, you also have to make sure that their lattice constant are very similar. So the lattice constant is basically the edge length in this cubic structure, something like this. And if they're not the same, then basically when you grow one material upon the other, defects will be generated at the interface. So that's why people have mapped this lattice constant and the band gap of a bunch of different materials. They find a very sweet green line over here. You can see from germanium to gallium arsenide to indium gallium phosphide, basically you have very similar lattice constant, and you can change the band gap from 0.7 to almost 2 electron volts. So that's why germanium and gallium arsenide are the most popular substrates for this high efficiency tandem cells. However, there's a big problem in terms of practical application. If you look at how's the cost of the single crystal gallium arsenide of germanium, that's about $10,000 per meter square. So we can never afford that. So these guys are basically making the world record of efficiency every year and being dispatched to Mars, but they're not really entering the market on Earth. So that's a very big issue here. Another interesting thing is that people find that if you slightly change the composition of these two upper layers, get more indium into those materials, basically you can get even higher efficiency. So this is what I proposed. If you have a germanium gallium arsenide substrate, you have these two layers, that efficiency theoretically can reach 59%, which is very attractive. However, there's a lattice mismatch nowadays. So that's something you don't really like. So we're thinking, because the lattice constant increases, how about I alloy germanium with a little bit of tin? Basically, I shift the substrate constant, lattice constant too. And if you get 8% tin to germanium, that's a perfect match. And what is more, if you can fabricate this high crystallinity germanium tin alloy on very inexpensive substrates like glass or plastics, basically that will throw away this $10,000 per meter squared into the away from the equation, and basically it will allow high efficiency solar cells to be implemented at low cost. So basically, you see that this is a solution to both cases: high efficiency solar cell and high efficiency data communication. So how do we address this problem? You remember, basically, in both applications, we need a certain degree of tin composition. The tin alloying has to be greater than 8%. As a material scientist, before you start to drive toward that direction, you actually check your map. Your map, in this case, is the phase diagram. So in the phase diagram, it's basically telling you how much B material you can dissolve in A, how well the two materials mix together. If you look at the phase diagram of germanium tin, there are two ways to look at it. One is a frustrating way. The other is a promising way. So I'll talk about the frustrating way first. Okay, take the phase diagram. You do what my students would do in 24. Okay, room temperature 300 K. I find the intersecting point over here, and I read how much tin can I dissolve in germanium without segregation. Unfortunately, that's only about 0.5%. So this compared to 8% is a huge gap. So if you want to increase this to 8%, that's actually an extraordinary effort. So that's why most people think you need extraordinary tools to implement that. So those extraordinary tools include molecular beam epitaxy, which is known to create some non-equilibrium alloys at high quality. But this is basically $1 million tool and very expensive to run. And also, this is still based on the fact that you should have a single crystalline template. If you're doing this on the amorphous material, it's basically wasting your money there. So we are taking another look at this phase diagram from a more promising way. We're looking at this eutectic temperature transition here. Once you're above this low temperature, which is only 230 degrees or so, you have a solid phase of germanium tin in equilibrium with liquid germanium. With liquid tin. So what that liquid tin offers is basically a much higher rate of atomic transport at low temperatures. So you can utilize that liquid phase to transport atoms such that it enhances the crystallization, enhances the grain growth, as we'll show you in the next few slides. And also, you worry about this equilibrium limit, solubility limit. If you want to break those kind of limits, one thing you should enter a regime where the basic assumption of this phase diagram doesn't hold. All the phase diagrams are based on the assumption of thermal equilibrium. If you go to a non-equilibrium state, then basically you have a chance to break that limit. So we actually beat this equilibrium solubility limit by crystallizing non-equilibrium amorphous germanium tin on dielectric layers and amorphous materials. And we're doing this deposition by thermal evaporation, and that's less than 1/10 of the cost of MB. So we achieve our goal, and we save Joe $2 million right there.
I like that.
Okay, so here are some results from our research. So initially, my student Highefficiency has tried to deposit this amorphous germanium tin on silicon dioxide dielectric layers, which is used to isolate electronic devices in photonic circuits. So basically, we do this co-evaporation, and what we found is that the crystallization temperature keeps decreasing with the increase of tin composition. So this is something we actually expected. Something we didn't expect is that actually these transition temperatures are very well defined. It looks as if it's a phase transformation. So once you reach that transition temperature, the phase transition, the crystallization can happen in just 60 seconds or so. And if you're below that temperature, it takes forever. Nothing will happen. So this crystallization process is really more like a phase transition in this sense. And after the crystallization annealing, if you're having a starting point of 9.5% tin, basically this is the X-ray diffraction pattern compared to the pure germanium. First thing you can realize is that basically there's an obvious peak shift. The peak shift to smaller angles is because you are incorporating bigger atoms of tin into the lattice. From that peak shift, you can actually derive that there's about 9% tin basically successfully incorporated into the germanium lattice. So that's far exceeding the solubility limit. And this number is also confirmed by Rutherford backscattering analysis. The second thing you realize is that if you look at the crystallization of pure germanium, basically the peaks are of similar order of magnitude intensity. Basically, there's no preferred orientation. But if you do with germanium tin, you have a very, very strong 1-1 peak. So this vertical axis is in log scale. So this is about 2 orders of magnitude larger than other peaks. So that means the material is really well oriented. And it's just by coincidence we have a model that's in exactly the same orientation like that. So it's oriented this way. 1-1 means the body diagonal of this cube here. So basically this is the orientation of the film. And we also did some analysis of the grains. So this is basically using electron backscatter diffraction. So each of these different colors of pieces means individual grain. So the scale bar here is about 5 microns. You can see basically you can get grain sizes about 10 microns long and a few microns wide. Compared to the film thickness is only like 300 nanometers. So usually if you can get a grain size in semiconductor films, if you get a grain size similar to the thickness, that's already considered pretty good. But this one is far, far exceeding orders of magnitude higher than the thickness direction. So that's a very nice crystallization process. Another interesting thing is that if you do a statistics on the misorientation between the grains, you'll find a very concentrated misorientation at about 60 degrees. Those correspond to what we call the twin boundaries. A twin boundary is basically like a mirror, where on both sides of the mirror, you get the mirror images of the crystal. It's one side like this, the other side like this. The important thing is that across this interface, there's no broken chemical bonds. So that's why the twin boundaries actually has very benign optoelectronic behavior. It doesn't really introduce the defects in the semiconductor material. We also have a small amount of low-angle boundaries. So these places lead to the tin segregation. As we'll show you later, if you see the growth more precisely, you can get rid of these small-angle grain boundaries, and basically you can get even higher tin composition into the material. We also analyze, what's the reason how we get such good crystallinity. So interestingly, if you look at this picture here, you can actually see the nucleation centers at different places. So this is a zoom in of the region 2, and basically you can see the crystal is growing radially from this nucleation center. And if you look at how distance, what's the distance between nucleation centers, basically you can see from this scale bar, it's about 1 millimeter. That's an astonishing feature because basically in the semiconductor thin film start to nucleate, usually the nucleation center is about a micron apart. So this is a very unusual behavior. And I think basically we find that this very sparse nucleation plus an extremely high growth rate due to this enhancement by the eutectic transition is helping this crystallization process. We also proved, whoops, I don't know what's wrong with this. Seems computer freeze. Okay, there we go. So we also proved that if you change the substrate to glass or even polyimide, basically the same kind of growth pattern will hold. So basically this kind of crystallization is really independent of the substrate. And this is actually basically the hands of Haofeng Li, my student. And basically, this is a deposition of plastics, in this case, polyamide. You can actually do this flexo substrate with high crystallinity germanium tin. And that basically provides a very nice template for future high-efficiency solar cells. So we want to move one step further. Can we really get single crystal material? Well, the key to get single crystal material is that you have to make sure you have a single nucleation spot, single seed to grow the crystal. So we developed two ways to do that. One is that you can use a nanotaper with a very sharp tip. If the radius is less than 50 nanometers, you can offset that transition temperature by more than 10 degrees. Then if you anneal the material at a temperature between the tip transition and the bulk transition temperature, nucleation will only happen at the tip, and then the crystal will grow laterally. So this is basically exactly the same figure I put in the proposal, and later, within a couple of years, we actually proved this concept is actually experimentally true. So this is basically the experimental data. We actually make this kind of tips. We also have references. This one is about 50 nanometer radius. This one about 100 nanometer. This is about 200 nanometer. So if you anneal the material, you find the crystal growth from this sharp tip is really dominant the entire structure. The one with 100 nanometers is actually getting less, and the 200 nanometer tip is actually having very little growth in this case. And interestingly, we find that all the boundaries, all the green boundaries here are twin boundaries. We do not see any tin segregation on the surface anymore. In this case, we can incorporate even more tin into the germanium, which is 11%, analyzed by micro-Raman analysis. So this nanotaper structure is also useful optically. They serve as an optical funnel to couple light from one waveguide to the other waveguide. So we can serve two purposes at the same time. Another way is basically accidentally discovered by Haofeng. And he was doing the micro-Raman analysis. He found that if you use the maximum power and he focused the light really well, the laser itself can actually crystallize the material. This is actually not a big laser you see cutting the steel. Basically, this is a laser with a power similar to this laser pointer. But basically, you focus the light so well to about half a micron diameter, you just quickly write through this. You can actually seed. You can do the nucleation with laser, and then you take the whole piece into furnace. Basically, the crystal will grow from the seed. You can see originally there were competing grains which are twins to one another. One of them accidentally wins and essentially extend across the crystal. So this is a piece of almost single crystal there. All the boundaries you have, we confirm, is twin boundaries. We also proved that the same concept can be used to improve the quality of blanket films. So just for fun, Haofeng has written two laser patterns, this square, this rectangle. You can see basically after the crystallization, these two guys serve as nucleation centers. So basically the crystal is growing out from here. Next question you want to ask is, how good is that material? When we talk about optoelectronics, light emission is something we really care. If you have a good material with optical excitation, basically when it's de-excite, it should emit light. So if the semiconductor material emits light, that means it has pretty good quality. So we actually performed this photoluminescence measurement at this is low temperatures. Actually, we do see the PL from the direct bandgap transition of the germanium tin. We expect that the pattern germanium tin will have even higher quality, but we're limited by the equipment. We don't have a micro PL system, but we will have that equipment arrive in March. So we'll perform some analysis on that part, hopefully getting even more impressive results. Another thing is that if your material can emit light well, and if you pump it hard enough, basically you can get into population inversion and even lasing. So in those cases, you can see a great increase in the transmittance of the material upon optical pumping. At Thayer School, we do have a femtosecond pump probe system, so we utilize those kind of equipment to see if there's any gain in this material when we start to do the population inversion. So this black curve is basically without pumping, measured by a regular IR spectrometer. And we'll start to do the pumping at low level. Basically, it converges with that data pretty well, except there's a slight increase in transmittance here. As you keep on increasing the pumping energy, basically you can see the transmittance near 2 micron increasing from about 30% all the way to 70%. So the materials get a lot more transparent. You can convert this kind of curve into the gain estimate. So you can find that basically this negative absorption over this region is basically optical gain. You can see that the material can actually get a pretty high optical gain on the order of 5,000 inverse centimeter. So this again proves the high quality and proves the potential for using this material for light emitter for photonic integration. And also, if you can make a laser with the semiconductor material, you can also make a good solar cell. So basically, this is proving the concept that this idea works. Oops. So now let's shift gear and start our second topic is basically light trapping in thin absorbers. So nowadays, the PV technology is trying to reduce cost while maintaining a high performance. So that's why you can see more and more of these bulk solar panels are being substituted by thin film solar cells. So thin films use much less material. It can be deposited on flexible substrates, but on the other hand, it has very limited absorption if you do nothing on the surface because the thickness is too small. So what we want to achieve by light trapping is basically to enhance the efficiency, making it physically thin but optically thick. So make a 1 micron film absorb as much light as probably 50 micron thick. So that's the goal. Conventionally, people have done this in several ways. One way is basically to use a textured transparent conductive oxide. Basically, that's a heavily doped oxide semiconductor material. So this material is transparent. It serves as an electrode for the solar cells. And also, you can actually control the deposition condition and etching to create some surface texture. When you have the surface texture here, when the sunlight comes in, it's going to be scattered sideways. So basically, that increases the optical path length of light inside the material. The downside, though, is that you can see this traditional TCOs are very rough. When you have a rough surface and you deposit active materials, you increase the area of that interface. Interface is never perfect. The more interface area you have, the worse the electrical properties. So this is why there's a limit in that sense. Another approach is basically to incorporate some silver nanoparticles or photonic crystal structures on the backside. The problem is that those structures that they're very efficient at certain wavelengths, but they're not really broad spectral. So the sunlight is very broad spectrum, so they can only enhance a small part of that absorption. So we were thinking maybe we can do something that combines the merits of the two approaches, which is basically instead of using the surface texture in the TCO, we can engineer some scatterers into TCO. So because the tin oxide is very commonly used, originally we were thinking that we can make it slightly tin-rich so that we can add additional tin scatterers inside the material. So that's our original thought. Oops, I don't know why it's got stuck again. Try to move this a little bit. Yeah. Okay, now it goes. So we start to do the experiments, right? So if you want to make a tin-rich tin oxide, basically you can co-sputter tin and oxide targets at the same time. So my students, Andrew Wang and Haofeng, was trying this for a while without too much success, too much interesting stuff, until one day they decided they will really crank up the tin composition. So all of a sudden, when they do this, they actually start to get very interesting structures. So the interesting structure is that when you do this co-deposition and kneading, you start to see some nano needles appearing in this case. So the left-hand side is basically a video. We'll show you the in situ formation observation a little bit later. But basically, we analyze this photograph also with backscatter mode of SEM. You can see some bright lines over here. Those are essentially the tin cores because they symbolize heavier atoms. So basically, this is like a core shell nanoneedle structure. And actually, they form in a very short time, as you see in half a minute or so. So you can see this is basically already showing up some features, and later this will grow very quickly. Within a minute or so, you'll form this kind of nanoneedle structures. Interesting thing is that this structure can be both N-type or P-type, depending on the needling conditions. If you're needling nitrogen, basically this is going to be N-type. Needling air is going to be P-type. And this is very rare in TCOs. TCOs are commonly N-type because of oxygen vacancies, but we can do both polarity. The conductivity is very good, comparable to the best in the market, and the fabrication temperature is reduced by 200 degrees or so. So you can see the nanoneedle formation in this case very clearly. So then we start to do some simulations to see how well this structure scatters light. Indeed, if you do the finite element Maxwell equation, you can actually see it does scatter light in a pretty broad angle. This is the case with the tin core, this is without. Basically, the scattering pattern are looking very similar, but actually if you calculate it quantitatively, the scattering efficiency with tin core is slightly higher, but it also comes with some loss in the visible regime. So we start to test our theory basically by doing some simple deposition, in this case on double-sided polished silicon. You can see basically the data agree with the experimental results very well. And we also predicted that if you apply on a germanium thin film, this can really enhance the absorption depending on the wavelengths by 15 to 30 times. So we made a diode using this P-type tin monoxide nanoneedle structure on germanium, on silicon. So indeed, we proved this is a very nice diode structure. This is a PN junction. Proved this is indeed heavily P-type. And also, if you want to measure the optical responsivity, we'll shine the light on it. In this case, 80 nanometer light. You see a strong enhancement in the photocurrent when you shine the light through this nanoneedle structures. Basically, that's enhanced by the light trapping. And this can be further extended to our applications in thermal photovoltaics. As we know, there's a lot of places generating a lot of heat, and those heat are basically wasted. So if you can recover part of that, that's a big boost to energy efficiency. So because the heat source usually radiates infrared, so you have to use small bandgap semiconductors like gallium timonide and germanium. But those, again, are very expensive. However, now we have the high crystallinity germanium tin on glass or plastic substrate. We can further couple this with light trapping using the tin monoxide, and basically potentially achieve very efficient thermal photovoltaic cells. So after getting this work done, we're thinking, how about we push the limit to see what's the fundamental limit of light trapping as we decrease the thickness of the absorber. So the extreme case is basically you do this on a single atomic layer. So in this case, we're doing this light trapping on graphene. Let me explain what this sample is. So when you deposit this single layer of graphene on silica SiO2 substrate, because graphene has very low absorption, about 1 to 2%, you do not really see that transfer layer. So my students cannot see that either. So Xiaobai actually just clamped the sample over here during the deposition. So this part has not been deposited silicon oxide nanoneedles. So the other places has been deposited, and after you anneal the sample to get nanoneedle structure, you see a very clear contrast. You see the outline of the transferred graphene layer, and if you extended that, you can see that basically this part should be graphene, and this part is the silica substrate. Without that deposition, you cannot see any difference, but with deposition, you can clearly see the contrast over here. And this is another sample we prepared, basically repeating the results. And you can see scientifically, this is because we have greatly enhanced the absorption of graphene by this kind of light trapping structures. So it increased by 10 times in the red and infrared regime. It's because more of the red light is being absorbed, so most of the color you see from the white light is like bluish. So that's why we have this blue shade over here. So can we understand it by optical simulations? Well, we just started to do this work. It seems there's a lot of tricky things here, but basically we can get a generally agreement with the experimental results. So this is the calculation. This black curve is experimental. And it seems that the field enhancement near this single layer graphene is very important to enhance the absorption. You can see this is not the optimal case because the highest field is still near the tin core. So if we further engineer the structure, we should be able to get even stronger enhancement here. But overall, it allows you to see a single atomic layer of carbon with light trapping. And the last topic, we're going to cover this solar thermal energy harvesting. So as I mentioned briefly earlier, basically solar thermal is a complementary technology to harvest solar energy because it's easier to store the thermal energy. It's also easier to integrate with conventional power plants because basically both are generating heat. And also optical to electrical conversion efficiency can be fairly good if you reach a high temperature. So that's about 34% in the world record compared to the limit, theoretical limit of silicon is 28%. So as mentioned, basically you need a very nice absorber material, basically absorb all the sunlight with very little radiation in the infrared regime here. So this is what we call a solar selective absorber. So it has to have a absorption curve something like this. So traditionally people were doing this work using what we call CERMAT structure. The reason why the metal tubes were reflecting light is basically because there's a refractive index difference between air and metal. So if you bridge that gap gradually using a graded layer where you increase the volume fraction of metal nanoparticles from top to bottom, basically you can reduce the reflectance in the solar regime. Because the substrate is usually a metal, so the light is not going to be transmitted through. So that's why if you have low reflectance in the solar spectrum regime, that means you have high absorptance in this material in the solar regime. On the other hand, you want to maintain the high reflectance in the infrared regime. However, in this case, you need a very precise thickness control, so usually it requires vacuum deposition. And the metal nanoparticles used in this case is very tiny, typically less than 10 nanometer diameter. So they're very easy to oxidize. So our approach is basically to introduce much bigger metal nanostructures and utilize the intrinsic optical response, that is, the free electron oscillation frequency inside the material, to efficiently absorb light. And because the optical properties is inherent to the nanostructures of metal, it doesn't too much dependent on the thickness in this case. So we actually can use very cheap chemical solution methods to fabricate these coatings. And we can also achieve anti-oxidation behavior, as I will show you in the next few slides. Okay, first talking about nickel, you may think you may feel it's a little bit strange because nickel, by definition, is something shiny like this, right? So actually, American nickel is not pure nickel. It's only 25% nickel, and the rest is basically copper. And there was even one time there's no nickel in the nickel at all. That was during the Second World War because nickel becomes a strategic material. So Uncle Sam was very rich at the time. They actually substituted nickel with silver, 35% silver in each of those coins. So if you collect the coins, make sure to collect those war nickels here. So how do you transfer this shiny stuff to black stuff that absorbs sunlight? Well, basically you can use the nanoparticles to help with the fabrication. So basically you can synthesize the nanoparticles using chemistry. So this is basically what you get. This is the solution. This is the powder. It looks pretty black. And if you look at the nanostructure here, after you mix this with a precursor and coat on the substrate, you can see this kind of nanoparticle, nanochain structures here. In this case, the matrix is aluminum oxide. And you measure the optical properties. Indeed, it has low reflectance in the solar spectrum regime, high reflectance in the IR regime. So how does that work? Basically, it's all talking about the coupling between light and free electron oscillation in nanostructures. So the light is an oscillating electromagnetic wave. So if that frequency is resonant with the oscillation frequency of free electron gas and metals, basically you have a strong absorption or scattering inside the material. That intrinsic oscillation frequency is dependent on the particle size. If you increase the size, basically it's resonant at longer wavelengths or lower frequency. That's exactly the same as all the musical instruments. You have shorter strings, you play higher notes and higher pitch. So that's exact analogy there. So we did this aluminum oxide work, and that looks pretty nice optically, but then when we put this sample into high temperatures, actually not too high, 450 degrees in air, we find the material actually oxidizes very readily in about 15 minutes. And we thought, okay, that's not so good. So let's try to see what we can engineer on the interface. I happen to have some experiences with silicides when I was a master's student. Silicides are conductive, high stability, and they're being used in practically every chip in our computers. Turns out that material is also equally suitable for increasing the thermal stability of nanoparticles. So we introduced a silicon-rich matrix. You know, silicon usually form oxide is from silicon dioxide, but we introduce a matrix that contains X equal to 1.5. That means the matrix is silicon-rich. And then we anneal the material before its operation in nitrogen at high temperatures. You can see the interfacial silicide formation. You can see the diffraction patterns of silicide on the interface. And now, if you apply this material to oxidation, so we're oxidizing at the same temperature. If you put this in the silicon-rich oxide matrix, basically there's hardly any oxidation at all. And we can compare this with different temperatures. So for this nickel silicon-rich oxide system, basically even at 600 degrees, the degree of oxidation is lower than nickel aluminum oxide system at 450 degrees. So it's very effective. Another thing we want to characterize is the optical properties. You find that basically the optical properties are very sensitive to the surroundings, to the oxidation surrounding the nanoparticle. Here's the simulation showing that if you have a very thin layer of silicide, basically that will shift the resonance. So we actually performed this kind of experiment. Indeed, we find that 450 versus 550 degree, we see an obvious shift in the spectrum. So then we think, okay, maybe we're going to completely oxidize this particle, which is only 80 nanometer diameter. So, but interestingly, we anneal for 12 hours. Basically, we can still see the nickel diffraction peaks from XRD. So Xiaobai decided to go another 20 hours at 550 degrees. We think now it should be completely oxidized. Yet, actually no, because you see the spectrum is almost identical in this case. We also want to verify if this is just due to kinetics, oxygen diffusion, or other mechanisms. So we make smaller particles. If it's due to kinetics, basically smaller particles will be easier to oxidize. However, we find the same kind of behavior. You know, oxidation basically saturates and terminates after 10 hours of oxidation or so in this matrix. So that's a very interesting feature. Basically, it's telling you that you could have self-terminated oxidation in this system. We also analyzed X-ray diffraction. You can see that between 12 and 30 hours of oxidation annealing, basically the spectrum are exactly the same. And you see this oxidation behavior compared to the kinetic model. So basically, this is certainly a different mechanism. Our current understanding is basically the interfacial energy must play a big role here. People have observed in the oxidation of silver nanoparticles that initially this Gibbs-free energy will decrease. But if your particle size is large enough, eventually the increase in interfacial energy, because you introduce extra interfaces, eventually this Gibbs-free energy will increase with the oxide thickness. So therefore, you're staying at this steady state over here. So that's a thermodynamically terminated oxidation. It's great for your stability for the system. And we think that probably we're having a similar case, especially we have a silicide around. And we also actually, from the Raman analysis, we find there's actually even strain in the silicide layer. So the increase in strain energy could also prevent you from further oxidation. So here's the conclusion slide. So we show you 3 cases, basically demonstrate the effectiveness of engineering materials for nanoscale light matter interaction to enhance the efficiency of harvesting optical energy and also use optics to transfer information more efficiently. So basically we conclude that nanophotonics is shining more light on the energy sustainability. And finally, I'd like to acknowledge our group members, collaborators, and all the sponsors from different sections. Thank you very much. Yes.
Almost question. I was curious,
Yeah.
in terms of solar cells or
Yeah.
interconnects, I started wondering what their lifetime is and what eventually causes breakdown?
What causes breakdown?
Is it material properties?
For solar cells, usually the lifetime is pretty long if it's inorganic material. So it's 20 years is usually not a big problem. If it's packaged well, usually it will not degrade much over time. One of the degradation mechanisms is the plastics that's covering the panel surface. Under UV radiation, that transmittance is getting lower and lower, so you start to get a shift in the efficiency that way. Another possibility is that your metal wires may get some accidental, corrosion of etching. So that's usually the major reason. Semiconductor devices very, very, very seldomly break down due to the semiconductor itself. Yeah. Yes.
You briefly mentioned thermophotovoltaics.
Yeah.
And I'm wondering what the target is as far as where this material would be useful as far as the wavelength and temperature.
Okay. So there's an interesting thing between. This is a very good question because harnessing thermal energy into electricity you can do two ways. If it's at a relatively intermediate temperature, like maybe like 400, 500 degrees, the radiation is not very strong, right? So in those cases, it's better to use thermoelectrics. If you have a very high temperature source, like 900 degrees, you have a lot of emission from IR outside. And if you want to put the thermoelectric material directly in contact at that temperature, it's basically a big stretch. So in those cases, it's better put your cells away from that heat source, basically harvest energy that way, right? So when we harvest solar energy, we didn't go close to the sun. Yes. Yes.
So you talked about engineering them to change the size of the nickel nanoparticles.
Yes.
And that impacted the scattering and absorption.
Exactly.
Right?
Yes.
But you described them as nanochains. You went really quickly. So.
Oh, okay. Yeah.
Nanochain.
So a nanochain is forming like this. So in this case, nanochain can actually self-assemble if you use the correct chemistry. Basically, if you use the correct solvents in this kind of reaction.
So they're interconnected, so they're chemically bonded?
There's some magnetic interaction because when we mix the solution, we use a magnetic stirrer. So in this case, the magnetic mechanism actually helps.
My question then is that what happens to the structure of the nanochains as you adjust the nanoparticle size? Does that have any impact?
Yes. So actually, we discussed that in the paper, but I later removed that slide because I thought it was probably too much to discuss. So if you have the polarization of light along the nanochain, basically depending on how many particles you have that chain, you can redshift the resonance. You can redshift the resonance to the extent where the length is almost equivalent to the plasma decay length of the electron oscillations. So beyond that length, basically because the plasma can only propagate so far, so it doesn't change the optical properties anymore. So the good thing, that's actually a good thing for fabrication because our fabrication usually lead to nanochains at least like 10 nanoparticles. It's pretty long. So in that case, you can actually further redshift the interaction. So for example, here I showed that if you just have single particles, wrong way. You have single particles in the air, basically you can have this absorption edge around 1 micron. If you want to redshift that to longer wavelengths, you can use nanochain structure.
I have a question.
Yes.
Am I correct in understanding, Jifeng, that the success of the 910 germanium having nuclear crystalline on top of an amorphous layer?
Yes.
That part of that success is having the nucleation sites separated by about 1 millimeter as opposed to micrometers?
Yes.
Why are they so widely separated?
This is something we're still investigating because I think we do need some in situ measurements to characterize that. My original thought, yes.
What do you think is going on?
We think it could be due to the undulations on the substrate surface. So whenever you have a small extrusion or something, that actually nucleates help with the nucleation.
So if you put it on glass or the polymer as you did as opposed to the SiO2, equally largely spaced?
Yes. Basically, I can go back to that figure. So you can see basically the similar mechanism holds, and this one to this one, the distance is about 0.3 millimeters or so. So the same mechanism holds.
Same explanation, you think?
I think it's possibly due to the, some irregularity on the surface randomly. So this is for my current understanding, because otherwise it's very hard to think that, how come we get nucleations so far apart. Yeah, it would be easier to understand why the lateral growth is fast because you involve some liquid phase, but nucleation is something we're still studying.
Okay, Jifeng, you have made me want to audit your class on advanced. I think that's my next goal. But
Okay.
thank you very much for your time.
Thank you.